Now, can you see my screen also? So what are we starting off with? So now what we're going to look at is the idea of, this is industrial organic chemistry. This involves things like crude oil. This involves things, I mean, I'm calling it industrial. It's what we have practical use for. Now, one of the most popular sources for hydrocarbons that we have is crude oil. Yeah. Now, crude oil is what? So, crude oil is what we call a fossil fuel. Now, what's a fossil fuel? A fossil fuel is literally made by living things. It's from the remains of sea creatures and land creatures that have been buried for over millions of years. They are the chemical evidence for life on this planet millions of years ago, because they were buried, they were alive, and then they died, and they were buried under, and then on the land, and they just died on the land, and then over time the things formed on top of that, and so on and so forth. So what we have is, over time, because of what you call it, pressure and conditions, things started to deteriorate, make them decompose, and they decompose to form things as a whole, which was mainly alkanes. They were hydrocarbons that got formed, but their mixture is what we call now crude oil. We mine it from the sea and from land, places like the oceans around the UK, Iraq, Saudi, UAE, Qatar, the lakes, Iran, all these places where we have had vegetation and human and plant life and animal life and sea life. They have decomposed over time to become what we call alkanes and alkenes, and we use them as fuels. But when we discover them, when we have to extract them, we extract them as crude oil. Crude oil is a very thick blackish liquid. I don't know if you've ever seen it in pictures. It is a quite thick blackish liquid. Haven't you ever seen? We've had crude oil spills in the sea which have left birds very, very, not very pleasantly, tarish. Yes, they are tarish in nature. Yeah. And that's that's the only way, because honestly, you cannot make these compounds in the lab. They're very energy inefficient to make in the lab, because they themselves are. So what are they? What are some of the properties these guys have? So fossil fuels for us are generally good fuels. They give us lots of energy, but they are a finite resource. But there will be some time that we will finish them, because the reason is we are not making this as fast as we're using it up. And like I said, this was made over millions of years. So this crude oil is a limited resource, it's a finite resource. It's great fuel, but it also contributes to global warming by producing carbon dioxide. How do you know it's a good fuel? Because the best reaction any hydrocarbon can have, be it alkane or alkene, is that it can burn in oxygen to undergo what we call combustion. And hydrocarbons make carbon dioxide and water. Even alcohols do that. But alcohols don't produce as much energy. But even alcohols burn in oxygen. And they produce heat. And that's why they're good fuels. That's what our use for them is. But they are formed as a mixture. So crude oil is a mixture. So you can think of it as a mixture of hydrocarbons. You're going to find both alkanes and alkenes in it. Mixtures, and the mixture ranges from CH4 all the way to, let's say, C25H52. I'm just guessing, somewhere as big as that even, or even larger, And that's what we have. We have C10, C20, 25, 35. It goes up to 30 tak, at least. And so they're really large, carbons. And their mixture is called crude oil. All right? So far, okay with you guys? Yeah? Understood. ऑल राइट, ठीक है. हम्म. 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 Okay. Now, so what we're going to talk about crude oil, we're going to do a few things. We're going to talk about how to separate each compound from this mixture, and the reason why we have the separation in the first place, because not all fuels burn the same way. So for crude oil to be useful, we first have to separate the hydrocarbons. So that's the first thing. For it to be useful, so to use crude oil, you know, it has to be separated, which have the hydrocarbons have to be separated. Now, and the easiest way to separate them is by their boiling points. And the reason why that matters is because, and this is a property of any homologous series in organic chemistry, which I already mentioned, homologous series बहुत पहले, is that as the number of carbon atoms increase in a molecule, so as the so when you go down this list, the number of carbon atoms are increasing, which also means their MR, or number of electrons, are increasing. Now what that does is it results in their van der Waals forces, which is the intermolecular forces. They become stronger. And if they become stronger, then what happens is that their boiling points, BP, which is boiling point, and MP, which is melting point, that increases. Like these guys are gases, this is liquid, and as you go larger and larger and larger, they become solids. So all of them have different boiling points, starting from below 0 degrees centigrade to above 100 degrees centigrade. Okay, and so we use boiling points to separate them. The process by which you use boiling points to separate is called fractional distillation. Distillation is using boiling to separate things. Fractional distillation is to separate multiple things based on their boiling points. So we call it fractional distillation. So that's what we're going to look at now, the fractional distillation of crude oil. And it might seem boring from this point, but it's fun though. Yeah. Mason, okay, it's recording on my iPad, and it's also recording automatically on YouTube, and also, so it's already been recorded 3 places, but I'll also do a Zoom recording. Okay, there you go. All right. Okay, it's fine. Zafan. Walaikum salam, Asma. How you doing? Yes. All righty then. Where are we? I forgot. Where are we? We are somewhere. Yes. It's okay, Mason. I was just telling you that we have multiple backups to put you at ease, huh? That his guys got his game on. They become a master and expert in this online teaching in the last 6 months. It's become, oh my God, I got like so much to do. Yeah. Sorry. My accent is coming out. It needs to go back in. Yeah. So what are we going to do? We are going to separate crude oil on the basis of boiling point. So we call that what? We call that fractional distillation of crude oil. Yeah, that's what we want to do. Now, why do we do this? We do this because what we realize is this. What is important is that first of all we separate them, and then we talk about their uses. That's what we do. Okay, so for example, is the most basic structure of this, which I will show you also. I'm just is that you take what is fractional distillation? Well, normally speaking, you heat up the whole compound. So what you take is you heat up crude oil. Okay? The basic principle is you heat it up, the mixture, and then you heat it so high, all of it vaporizes. You want all of this stuff to vaporize. Now when you heat it, it vaporizes. What does vaporizes mean? They all become vapor. And then what you do is, the further away it goes, the colder it gets. The cooler it gets, then it starts to condense back down. So it goes up as vapor, but then it starts coming down because of condensation. Because the further away it goes from the heat source and it generally hits other areas, it starts to cool down, because the moment it boils, it vaporizes. So if it's going up, if its boiling point is very close, then it starts to condense back down. And the ones whose boiling points are still far away, they'll keep rising and rising and rising. So for example, the ones that have very, very high boiling points, and let's say you heat this and you have high and low boiling points. So the high boiling points guys and the low boiling points guys can rise to different heights, because if you heat the low and the high, the low is already vaporized and the high starts to vaporize now, because they take time to vaporize and they're high boiling points. So when they finally vaporize, the moment they move a little further away from the heat source, they cool down. The moment they cool down, they go back to being below the boiling point, so they condense back down. The ones that have low boiling point, meaning what I mean, low boiling point is, let's say 100 degrees, and high, I mean 300 degrees. And let's say you heat this to 400 degrees. So everything vaporizes, but that 400, as it goes further away, cools down to 300, to 299, and suddenly the 300 guys will deposit. But the 100 degrees will still keep on moving and moving and moving till you go up till here and you say, okay, now it's cooled down to 100 degrees, and then they will condense back down. So the ones that have a higher boiling point condense down closer to the heat source. The ones that have a lower boiling point condense back down higher, further away from the heat source. And some you actually just collect as gases. You don't even condense back them down. They have such a low boiling point, they're actually gases, and they then are collected separately. So we collect at different boiling points different mixtures, or different number of carbon atoms. This isn't the purest way of making it, because at every point you get a mixture of hydrocarbons, but at least it separates them somewhat. So anything that gets out of, let's say, port A is, let's say, carbons 15 to 35 or 30, for example. And here is carbons 5 to 14, just as a rough estimate. And this is carbons 1 to 4, the ones with really low boiling point. And so in the real world, we have more divisions to even separate them further. But that's the basic principle by which they react. All right? So no, by which they vaporize, not react. What was I saying? Vaporize. Making sense so far to you guys? Yes, petroleum is crude oil. Yes. Petroleum, I think, is the cleaner version of crude oil. Okay, 1 second. I'll show you something. So let me show you one such column. Now every book has a different word diagram, but they all mean the same thing. In the real world, we take a crude oil. Okay, now crude oil is actually a more unrefined version of petroleum, but crude oil can be considered petroleum. All right. So the temperature does change. Yes, it gets cooler, so we have to continuously heat it. So what happens is, this is where you take it, you preheat, you get through a preheater, which then heats it. And then once you get in this column, they start getting heated from here. So when they start getting heating from here, they start rising up. Now, the ones that have very high boiling points, the ones that will high boiling points will literally condense faster. Low boiling points condense slower. So the very high boiling points are guys with more than 25 carbon atoms that have a 350 degrees boiling point. They will condense down. So these are trays. These are trays that help us condense. So these are like air gaps that they come here, they condense. The gases go up here. Then they come and more condense right here. So this might be temperatures of 330. This might be temperatures of 290. So 300 and deposit here. This might be temperature of 240. So each of these sections have a different temperature. Even the column is industrially designed so that in the lowest temperature here is high, like 350, and then as it goes up we decrease the temperature. So at different temperatures different things are condensing. And so first the highest boiling point, then lower, then lower, then even lower, then even lower, then even lower, then those are gases at room temperature. And each of these portions that are taken out is called a fraction. So each of these are fractions. The fractions are not an actual molecule, they are a range of molecules, because a few, like gasoline is C7 to C9. So that means the petrol in your car is not just one alkane, it's a mixture of 3 alkanes, because we don't need it to be one alkane, all 3 will vaporize, or all 3 will combust. So heptane, octane, nonane, meaning petroleum can be a mixture of, petroleum, petrol is C7H16, C8H, what is it? 18, and C9H20. So for example, this fraction will be these guys. Naphtha is slightly more than that. Kerosene is even greater than that. Then we have gas oil, heavy gas oil residue. Multiple books call them multiple things. So I want to show you other diagrams also from different books. So I wanted to show you that. This is from one of a fractionating column. Some call them petrol for cars, some call them jet fuels and diesel. So the idea is simply this, that you start off from the ones that have the lowest boiling point. That mixture is used for gases. Then right after them is what we use for car engines. Then we have for chemicals. Then we have for jet fuel and diesel car engines. Then we have lubricating oils, and then ships fuels. Because you see, ships are so large they can burn a very large hydrocarbon. Cars, for them to burn a large hydrocarbon, the car engines need to be really large. That's why, by the way, diesel engines are really larger than car engines. And this guy is bitumen for roads and for roofing and other stuff. We use the black thing on the cars, on the roads, basically. So, okay, so light gas oil is also known as diesel oil. This is kerosene or jet fuel. So multiple will have, so you need to remember that gasoline can also be called petrol. Naphtha is for chemicals. Kerosene is for jet fuel. Light gas oil meant diesel oil, and then heavy gas oil is used for other things, what you call it, fuel for ships, other things. And bitumen is residue, is used for roads and road carpetings. Yep. Yes, Dilavar, I am back. Your girlfriend's back, honey. You are more excited to see me than your own girlfriend, I think. I didn't realize caused that much excitement. I would have, no, I wouldn't have come earlier, but I had reasons to not be here. But you guys get the point. Yeah. Ramesh, what the hell? What happened? Somebody made a joke and chat, and there was only panelists, so the hell was that Dilavar made a nice joke. You're back finally with like 18 explanation marks. Hence. What the hell? What is what the hell, Mike? What the hell is such a rude thing to say? What the hell? You see her every day. Okay, that's so. Yeah, okay. Yes, absolutely. She'd love to hear that from you. Hey, I see you every day. Uh, Chalo, whatever the reason is that I am much more excited about. Yeah. Hi, Ramis. What's up, Ramis? Okay, so I'm showing you another picture now. Just no. Actually, there's another. I would replace the hell with another word, but I can't do that here. It would be impolite. Man. It's a couple of letters before H, you know. That works. Anyways, where are we? I'm lost in my screen. My screen. I'm great. Jasneet, Ali Hamid, who I was watching, Asma, Zubair, Rimsha. All right. Moving on. Can I continue? So this is a much more fun way to look at it. So you get a crude oil, you heat the crude oil, it becomes vapor, and the heavier guys stay low. They become road surfacing agents, fuel for ships, then diesel cars, then jet fuel, then chemicals के लिए naphtha, then petrol, then basic gas like methane, natural gas, LPGs, butane and propane. So longer chain alkanes here, shorter chain alkanes here. The shorter chain alkanes are actually much more useful. Chemicals and petrol for car and jet fuel has more uses than these things do. But this is what drives all of our industrial revolution. Right here. All right. Okay. What else? You guys get that point? Okay, so where was I? So ye ho gaya. Then what do we have? What next? Okay, one thing. One second. Okay, now this part done. All clear? ठीक है. No, Ramis. I don't know that meme. Could you share that with all of us in the group? This, if you can find it, share it. You know. All right. Thank you so much. No videos, 10K subscriber challenge guy. I'm so glad I could help you out, son. Okay, or daughter, whoever you are, whatever you are. Sorry, I meant was like, all right. I'm so glad I could help you out. That's what the channel is there for, to help people out like you who need help. Anyways, let's go on. Ramis said something to me in private, but he doesn't want me to share with anybody. Okay, moving on. So उसके बाद मैंने क्या बात करनी थी आपसे? हाँ, next up is cracking. So basically I had a table here somewhere. Where did it go? Sorry. It went somewhere, no? Oh yeah, sorry. One second. And a nice little table I wanted to show you. Okay. So now I want to discuss some. So now I would like to discuss some economics. Okay. About organic chemistry and crude oil. Thank you for that compliment. Yes, I'm trying to be a bigger legend now, and recommend my channel shamelessly to everybody you know. It's free. It doesn't need any subscription, you know. Anyways, guys, getting back here. Where was I? Now, the economy of organic chemistry. Now, the thing with that is, there's something that you need to understand, is that we have shorter chain hydrocarbons and longer chain. We even separated them in the crude oil fractionating. So, you need to first understand how the properties vary and their uses therefore vary as the molecules get larger. As the molecules get larger, their boiling point will tend to increase. It gets higher and higher. So as the molecule size increases, the boiling point at which the liquid boil increases, which means the volatility decreases. So as greater volatility when you are small, like you vaporize easily, like petrol will vaporize more easily than diesel would. And when you are smaller, you are what we call very viscous. You are very runny. But you know, as you become, so you're low viscosity, your resistance to flow is low, is very runny, like petrol. But as you go higher number, longer chains, you become thicker. And when you become thicker, then the last thing that matters is flammability, meaning how easily it burns. The smaller cars burn very easily, like home gas burns extremely easily. But diesel fuel or even bitumen or wax burns really slowly, and it even makes a smoky flame. So if you notice, the cars that give you a lot more black smoke as diesel cars do, but the gas burned at home, methane gas, has no black flame generally. But if you ever use kerosene oil, if they play kerosene oil, burn kerosene oil, you blacken your pots. And the reason for that is because kerosene oil is larger carbon chain and they have low flammability and greater smoke. Matti ka tel, like you call it in Urdu. But the gas from your gas lines is highly flammable. So the point is that there are certain properties that shorters have, the certain properties that longer have. These are more desirable properties as fuels. That means these are more expensive. So these guys have what we call high demand. The lower chain, shorter chain hydrocarbons. Thank you. All right, awesome. Yeah. Thank you, whoever's online. Ramesh, it's an hour class, Jaws. I have actual class at 7 o'clock, so it's not an hour and a half. No, Sunny. Okay. Moving on, can I? So do you understand these properties at least? Yeah? Now, so because of this high demand for lower chain alkanes, we want to be able to, the idea is that the lighter fractions are in higher demand, and heavier fractions not so much, are in lower demand. So what we do is we take the heavier, larger hydrocarbons, could be alkanes and alkenes, and we convert them into smaller or lighter hydrocarbons. And this conversion process is what we call cracking. Cracking. We crack hydrocarbons because some of the heavier fractions are not in high demand, but the smaller ones are. And the reason why they're not in higher demand is because they're thicker, they're harder to burn, they are solids, they don't vaporize, they're not much use for us. But smaller guys are. So we figured out a process where we can take larger molecules and break them into smaller molecules. Literally that. Literally take a larger molecule, make them into a smaller molecule. That's what we call cracking, crack-a-lacking. And cracking is a process that can take a very large molecule and make it into smaller ones. The smaller ones, I mean, it's not a controlled process. So you can have random processes. So for example, you can take a guy which is, let's say, 1 2 3 4 5 6 7 8 9 10, and you say I can crack it into a 4 carbon fellow, a 3 carbon fellow. This is, no, let's put in more, like to say. So 1 2 3 4 5 6 7 8, let's make it 9 and 10 and 7, and a 2 carbon fellow and a 1 carbon fellow also. But at the same time you said no, some of those could actually just become a 5 carbon fellow and a 4 carbon fellow and a 1 carbon fellow. At times it could also make a 4 carbon, a 3 carbon alkene and a 3 carbon alkane. Also do that. Alkenes, it's a mixture of alkenes and alkanes, sorry. So I should correct myself that most of these will be alkenes. Most of these will be alkenes. So there is no rule. You could also have made 2 guys only. So this guy could have made one 6 carbon alkane and a 4 carbon alkene. Now I'll show you how you can figure this one out. But it obviously the total products can number of carbon atoms have to equal to the starting number. And nothing is added or lost. It's literally like this. If I had to make an equation, the one on top, this one, let's call them equations. Let's say 1 2 3 4. All these are possible reactions converting C10H22 in option number 1. I made into C4H8. I made into C3H6. And I made into C2H4 and CH4. And the way to check is you add all the carbons, they match up to this, meaning 4 plus 3 7 8 9 10 carbons, and hydrogens 8 plus 6 14 plus 4 18 plus 4 22. But that was just one of the equations. The second one could have been, let me just move this up first, sorry, right here. And the second equation could be that C10H22 can make C5H10, C4H8 and CH4. The third equation could have been C4H8, C3H6 and C3H8. Just to prove, add 4 plus 3 plus 3 is 10 carbons, 8 plus 6 plus 8, 8 plus 6 is 14 plus 8 22 hydrogens. The same exact formula. The point I'm trying to show you here is that the same hydrocarbon can make on cracking so many different molecules, C6H14 and C4H8. All these are possible. So these are examples of cracking a 10 carbon hydrocarbon. And we use cracking by using heat, a catalyst, and high pressures. But generally heat and catalyst will work. So if you take heat and catalyst, it will work. And this is called catalytic cracking. You don't need to know the name of the catalyst. It's a transition element. It's a catalyst, and it will make a large chain alkane into multiple smaller chain alkanes. So if you have 100 molecules of this guy, maybe 30 will do this, 15 might do this, 18 might do this, and the remainder might do this. It's all random, so much random. So as long as you make up the final product in the number of carbons and hydrogens, that's how you get small chain alkanes from a larger chain alkane. I'll tell you a trick to figure this one out. So whatever a hydrocarbon you burn, so let's say you burn a large hydrocarbon, okay? Especially if it's an alkane, especially has the formula CnH2n plus 2. Remember, it will only make one alkane and remaining one or more alkenes. That's the key. So for example here, alkene, 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 alkane, alkene, alkene, alkane, alkene, alkene, alkane, alkane, alkene. So one made 3 alkenes and an alkane, 2 made 2 alkenes and an alkane, 3 made 2 alkenes and an alkane, a different alkane, and 4 made 1 alkane, 1 alkene. The thing with that is there is always only one alkane, always only one alkane, and the remainder can be 1 or 2 or 3 or more alkenes, whatever you like. All right, and this is the process of cracking, and you are expected to take a hydrocarbons and write the equation of cracking. That's it. So it could be any. So if they said write an equation for the cracking of this fellow C10H22, you could have given any of these 4, plus I'm sure you can come up with some more for yourself to give them as cracking. All right. All right, any questions about this? You clearly didn't miss me. You showed up 54 minutes late. Agastya. Okay. Anyways, Amna, Ramesh, Haya, Ariba, Arisha, Haya, whoever else is here. Any questions? One example question of cracking? Yes, I could do one example question of cracking. I could absolutely do one example question of cracking. If you give me a minute, I will do it. 1 second. See, I got to find the past paper equation. So let's say I will find my O levels. Okay, and I will find my question. Hi Arib, there's Arisha also. Arib, and there's Arib too, and Arisa too. Okay, don't tell me it's only you. Okay, now I got to find cracking, huh? I'll have to find it. Maybe let me show you some more. I'll do one more. I can't find it, Abhi. Okay. Now you can also guys make multiple alkenes only and even hydrogen. So for example, C10H22 could be C5H10, like this fellow, No, let's make it, no, let's make just like this. Instead of C4H14 and C4H8, it can be the C6 ki alkene and C4 ki alkene and even hydrogen. Even that can also happen. So sometimes cracking can also make hydrogen. Yeah, and that's something, and that is possible. All right. Yeah. Like then, and a question that you might get is like this. Okay, so I have a molecule C11H24, and it cracks into A, B, and X. Sorry, 3 products, and they say X has an MR of 98. What is X? Well, how does one find out? Since you know it will only be hydrocarbons, how would you find out X at least? Forget A and B, but X. How would you find X out? Well, very simply, the MR will help you. You see? How? Well, since the X can only be a hydrocarbon of CXHY, then it's got to have carbons, right? So what you do is, you take 98, and you know carbon's mass is 12. So you see how many carbons can I have in 98. How do we do that? Simple. 98 divided by 12. Does someone have a calculator? Tell me what that is. So 98 divided by 12 will give you 8.16, right? So what I'm going to guess is there are 8 carbons in this guy. If there are 8 carbons in this guy, how many hydrogens? Well, then you find the mass for 8 carbons, which is 8 times 12. What is 8 times 12? 96. Now, you cannot have C8H2, can you? Because 96 is carbon and 2 is hydrogen. So you're like, wait a minute, it can't be C8H2. Then what do? You check the next guy. So if it can be 8 carbons, how about there's 7 carbons? It's trial and error. So then you say, okay, it might have 7 carbons. When you do 7 carbons, that's 84. And total is 98. So what's 98 minus 84? 14. So therefore X is C7H14. All you had to come up with was going to be smaller than this guy and make up a mass of 98. So this is a trickier version of the question, but this is what you can expect. All right? Got it? Now I've got to exit. I have a class with the other kids for A levels. I'm gonna head out, but tomorrow you'll see me again. Okay? And tomorrow we'll do past papers on this and others. Is that okay? Can you hear me? Yeah, you can hear me. So yeah, is that all right? I'm gonna head out now.